conditions of that magnetic stuff locked in the rocks, and they made maps. And they saw these patterns in the maps, and the patterns were symmetrically disposed over these big mountain ranges. They go, what the heck does that mean? I mean, it was like somebody screaming eureka. It's like the mathematics thing I saw on PBS last night about numbers. It was great how the number 1 and 0 came into being and all that stuff, and eventually led to computers. It's just wild how all of a sudden, oh wow, look at this. Some new insight to stuff, and that came up, these positive and negative anomalies in these patterns. They went, you know, what does that mean? Patterns in anything. Isn't there a TV show out there that's called Numbers? You start looking at patterns and stuff. Patterns, you can do it a lot in any discipline. They brought samples back up from the ocean floor and age dated them. They went, you know what, as we move away from these big mountainous rift systems down there, they get symmetrically older away from the ridge. Ooh, another pattern. Let's go get some more data. Let's core the sediments that sit on top of the basaltic crust, and it turns out that right over the ridges you hardly have any sediment at all. And you get further and further and further away, guess what? Symmetrically the thicknesses get thicker and thicker and thicker of those sediments. So all of a sudden patterns were flying, and somebody says, something's going on down there. We go over the middle of these mountains, we drop the heat detector, it's real hot over these mountains down there, really warm temperatures. And if we measure the crust further and further away, they get symmetrically, key word symmetrical here, they get symmetrically colder and colder and colder. And as rocks get colder and colder, they get what? Denser, so they're going to sink down. Why are those ridges topographically high? They're hot, they're buoyed up, they're less dense. And one thing led to another really quickly in this process, in probably just a few years. Within 2 or 3 years, I mean, research went crazy. And papers were written, and arguments went on, and this simple idea that the seafloor is split and open really led to something very quickly. Gravity measurements. A gravity measures density differences. And if you go over a rift system, those high mountains, they were real high gravity values. Well, why? Because we got this dense rock closer to the surface of the earth. If we go to a subduction zone or a trench where the thing's moving away, its mass is moving away from the gravity meter, if you have any little physics at all, you know that that's going to lower the value of gravity. And these are just some of the things. Okay, this is a list of some of the evidences that really led and opened this idea to say seafloor is split and open. It's spreading. And someone said, you know what? That must be the mechanism for Wegener's continental movement. Spreading things away. Another thing about the age of the ocean basins. If we measured how old the rocks are, the oldest rock was in the Jurassic period. Now that's not very old geologically. That's not very old. They said, well, how come the ocean basins are so young geologically, from the rift to the oldest wide part away from the rift systems, and yet on continents, rock mountain masses some places and the cores and the shields of continents are, you know, very, very old. 4 billion as opposed to maybe Jurassic around 180 million years old, let's say. That's a huge difference. Someone said, well, you know what? Maybe in these spots where the ocean crust is meeting certain continents, it's going back into the earth. Maybe it's being destroyed. These were questions they asked. We now know that that's what's happened by additional research. So let's take a look at some of this magnetic stuff. On the land, okay, here's some layers you saw earlier in this class out there in the plateau stuff. Layer after layer, 15,000 feet thick of lava flow, lava flow, lava flow. And we age date those, and then we look at the magnetic data locked in the basalts, and we see the reversals plotted up in a vertical pattern, put them in a chart, and this is what we see. Now we've seen this kind of before already, if I'm not mistaken, talking about the magnetic character. And you see the positive and negative, and that little strip on the left here, this color stuff right here from this younger bronze layer down to older, 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 it looks like a barcode. Now, gee, wouldn't it be neat if we could, we could measure this on land? What would happen if we went into the ocean basin and did the same thing? Would the ocean data match the land data? Well, it did. Perfectly in age and reversals. And they all pointed, too, by the way, to the same singular magnetic North Pole in this case. So out in the ocean basins, we use kind of the same names, that if we begin on the top and start it and just give some color patterns to the reversals, notice how symmetrical they are. Now that's a cartoon. That's a nice, neat drawing cartoon. Here's some other neat new pictures in your book about patterns that look a little more realistic in terms of this. There's that ship over there on the left, and the magnetometer instrument there on the back of the ship. They drop it over the back and then just drive across these and get a chart like this in terms of positive and negative character. And propose an idea that, a continent splits open, gets wider, and see the symmetrical patterns. That's just magnetic data. They've said nothing about anything else yet in the list. Now here's a more original map. Now it's not that perfect textbook looking symmetry, but it's pretty darn good. The first place they saw this was in the North Atlantic. A group of fellows named Vine and Matthews and a gentleman, I think it was Morley from Canada, a graduate student, who proposed this too. Seafloor spreading. So here's one off our west coast. Got names to them now. The rift system is running kind of down the middle here. There should be a darker black line I could have put on here. But they're symmetrically disposed on either side. Rocks get older away, so they start coring the data, looking at the fossil evidence, matching up these patterns. We know that away from a rift, the sediments get thicker and thicker and thicker and thicker, and they get older and older and older, as do the rocks, the basaltic rocks underneath. Start putting this in a map pattern and go, wow, look at these patterns. Some parts are moving faster than others, so they're kind of offset. That's our transform faults we'll get to a little later on. But the oldest crust is these blue areas, or greenish blue, I guess, on the screen up here, of crust. At the very edges, as far away from these rift systems. These dark black lines represents those high mountain ranges. This is the East Pacific Rise. Over here in the Atlantic, this is the Mid-Atlantic Ridge. And notice how the alignment of these ridges almost parallel the shorelines of the continents. Same thing, they fit. It's really cool. And I haven't even talked about some of the significance yet of what this means in terms of economic deposits. From a standpoint of evolution, we'll come back to maybe a little bit of it later on in the semester. Heat flow measurements, kind of a busy looking diagram here, but where those hot spots are, here we are, the East Pacific Rise on the left side of the diagram, the Mid-Atlantic Ridge. All those rifts where it's the hottest. It's brand new crust, magma coming out of the upper mantle. Gravity measurements again, especially the ones where we got deep sea trenches of slabs of rock going back into the earth. Uh-oh. I have a feeling when I clicked on this, it's going to want to go to a website on me. Yeah, it did. I'll get out of that and click it on. So we'll get back to this picture again. So here's kind of the common picture you see in the textbook. We have lots of big names. For example, here we have, again, the North American plate. It's moving westward. The rift that's driving it, the speed of the rifting is what controls how fast the plate's moving to the west, and also if there's something slamming into the other side. It's vector forces and moving mass, that's all it is. Like I said, a giant demolition derby. When the Cocos plate down here moves away from the East Pacific Rise, it moves eastward, it goes underneath Central America. That's what made the land bridge between the continents. The Nazca plate, when it moves towards South America, crumples up that western margin, makes the Andes Mountains, the earthquakes, the volcanoes, all that activity. And of course the Pacific plate is all to the west of that East Pacific Rise and then moves all the way across, so it gets colder and colder and colder and colder. I'll come back to that just later on. I'll show you a picture what that does, what that means. All right, so plates. We've divided up this brittle outer part of the earth, like go get yourself a stone plate and drop it and bust it all up and now put it together. Sometimes you can't find the pieces, and at least you can see the margins between them. Those rift systems are the splits in our plates. So we've got these brittle, sometimes they're semi-brittle, but pretty much a brittle nature. A singular plate is defined as a mass of brittle to semi-brittle rocks all moving in the same direction. Like the North American plate is moving westward in some general compass direction, which you don't need to know. The Nazca Plate is moving in some particular direction. But they're all moving at the same approximate rate, same general direction. Now, these plates can be solely an oceanic chunk, like the Nazca Plate, or they can be maybe a sole continental chunk, like the Arabian Plate, or they can be both, continent and ocean. South American Plate is continent and oceanic. North American Plate. And you can just look at the map to see which ones are which. I'm not going to make you learn the subtleties of that. But again, these materials make the various types of masses that we see are continental plates. And here's a diagram of it from your book. What they want to focus on with this picture out of your textbook are, here's the East Pacific rise, and then they got a little inset of, well, what kind of plate margin is it? Here it's pulling apart, called divergent. Where the Nazca Plate's going underneath South American Plate, collision, the Nazca Plate dives down in a subduction zone, so they're hitting head on. They're converging, so they call it a convergent plate. They pull apart by tension or they converge by compression. Okay? Or they might slide sideways past one another. They show you down here in the south part of the diagram between the Antarctic Plate and part of the African Plate in here. You got a sideways motion going on with that plate boundary. They call it a transform fault. We saw a little bit of that earlier. We'll come back to it again, and I'll reiterate that because there's a more famous transform fault up here in California called the San Andreas Fault. So plate boundary types. Divergent, usually where the mid-ocean ridges are splitting apart, or in some places on the continents, like the original Pangaea, they rift apart. Convergent plates, those are where they're hitting head on. You tend to get large volcanic arc systems like the Aleutian Island chain, the Japanese island arc system. And I'll give you some specific examples of those again. So divergent, convergent, and lastly what's called a transform. And I'm using the word shear or shearing here. That's a sideways, kind of mostly horizontal type of movement. And the more famous one, there's a book out there, Crack at the Edge of the Continent, a new bestseller. It's all about the San Andreas Fault, but it's much more. I just started reading it a couple weeks ago, and it's a unique book. It's kind of fascinating to get into history stuff too, about the West and the gold mines and how San Francisco came to be what it is. They're well written. So these are the three major plate boundaries: divergent, convergent, and transform. Let's take a look at those first ones. Divergent oceanic rifts. What you have in a divergent oceanic rift is a central drop-down rift valley. Okay, they call it a valley, a central rift valley. The tearing apart, the pulling apart of oceanic crust creates earthquakes that are fairly shallow. They're not real deep in the earth. They're small-scale, near-surface faults in those brittle oceanic basalts. So shallow focus is the way we look at that. And the most main rock type involved here is basalt. Oceanic crust is the partial melting of the upper mantle. We learned earlier in this class, chapter on igneous rocks, that's mostly basaltic. So main characters of oceanic rift systems. So the Mid-Atlantic Ridge. The Mid-Atlantic Ridge is a modern-day example of a divergent rift system. What about divergent continental rift systems on a landmass? Well, the main one I'll show you more pictures of is East African rift system. There's one that's not active anymore that was in part of the United States through New Mexico and down into Mexico itself and a little bit up into southern Colorado, called the Rio Grande Rift. You go down and you can see all kinds of volcanic activity, lava flows and little cinder cones and stuff. We'll focus more on East Africa in a bit. this is the very beginning of Pangea splitting up. This is the opening up of a continent, the opening up of a brand new ocean to fill in that downdropped, split apart crust. If it drops low enough, seawater inundates and it becomes a small seaway. But what if it doesn't? What if it stops? What if it fails, okay? There's a new word for your vocabulary, allocogen. This will certainly be on the test. An allocogen is a failed rift system. And you know a little bit about one already, you just may not remember it, and I'll show it to you again later on. It's a failed rift, an allocogen. Rock types, again, you'll get basalt oozing out, but you also got terrestrial rocks forming in this basin, sandstones, conglomerates, certain kind of sedimentary rocks you already learned about in the class. But you do have this basalt mixed in. That's emanating from the upper mantle. Now we're going to look at some of these again in a little more detail coming up here in just a bit. So the East African Rift. Here's a continent that's splitting apart. Okay? So as it Pangea or Africa or North America, any continent begins to split up, you get this upwelling of magma. The tensional forces pull it apart, it splits. So you get a little doming effect in the beginning. But eventually, as magma comes up and it splits further apart, it drops down. It's a series of normal faults that are being formed by it pulling apart. And if it can drop low enough below sea level, you'll get a small seaway. So what we're seeing right up here in the second choice, that's kind of like the East African Rift today. Right here, this is like the Red Sea today. And the bottom one would be like what? The Atlantic Ocean. And we could name any ocean scenario to this process in talking about the breakup of Pangea, which I won't. So there's the same picture, the same sequence on the left. Here is kind of like an upwarping along that coastline, okay, in Nigeria and parts of Brazil. And the first beginning little mass of water in there, seawater, salty deposits, marine rocks, evaporites developing, okay. Splits a little further apart. Now the species are separated. Eventually we're getting further apart in here, like in the bottom left. And of course today it's thousands of miles apart. Let's zoom in on East Africa. East Africa's got a triple junction. Remember I had something way back when about basalts that get columnar basalts? And the little cracks that develop in there, the columns are 120 degrees apart, arc degrees. Here's the same thing. The Red Sea is one arm, running this way. The Gulf of Aden's another one, and running down the east side of Africa is the third arm. They're all about 120 degrees, arc degrees apart in what we call a triple junction. They're all splitting apart. Saudi Arabia, the Arabian Peninsula, is moving northeast and slamming into southwest Asia. The Zagros Mountains up here that border these countries in the Middle East, in terms of Iraq, Iran, Afghanistan, Turkey, and all that, that's all a result of that crumpling. And the squeezing and compression and development is what created all these oil deposits up here in that case. The Gulf of Aden is splitting open, and right now on the land this is all splitting open. Some are occupied by long linear lakes. There's all kinds of lavas in here. If you fly over it, here's the Red Sea right up in here. Down here, these dark patches, those are volcanoes. You can slide this little lowland right underneath the tip of Saudi Arabia. The rock ages, types, fossils, everything match up perfectly. The top part stripped off and moved in part, became part of the Arabian Peninsula. What got exposed is this lower down stuff. But you can move that back in there and it fit perfect. Trying to make the broken pottery get back together. More pictures of the same theory. So it's a pretty active continental rift system. Well, back here at good old North America, we've got some other ancient rift systems you may not even be aware of. You may drive across some in Kansas and not even know it. That at some point in our geologic past, mechanisms going on in the upper mantle was trying to split North America apart a long time ago. But the energy died out and it didn't work, it didn't split. But there was magma that came up. In fact, some of it had some water in it. I'll bring your attention to a couple places. One up here by Wisconsin, Upper Michigan, the Keweenaw Peninsula, Isle Royale out in Lake Superior, Minnesota. That dark patch of rock as you come down, you can trace it all the way into the subsurface of eastern Kansas. You can drill down and find the same rocks under Kansas as you do up here. They're basalts and they're gabbros. And they have pillow basalts, i.e. submarine eruption going on. There's one down here in southern Oklahoma. There's one here in southeast Missouri into Illinois. Here's one you've got to learn. And this map inset on the bottom right is there's multitudes of old scars, old rift scars that just didn't do it. Not enough energy. So the one you have to learn for this class that runs down up here from up, like I said, in Minnesota, upper Michigan, down underneath Kansas, is called the Central North American Rift because it's running down the central part of North America. And it's an ancient rift, but it quit. It's an alocogen. It's the acronym, of course, is CNAR, CNAR, and the CNAR is an alocogen. Several thousand feet below eastern Kansas, you can drill down and run into these basalts and gabbros. Same age, same stuff as up here that you see exposed. They're exposed now because they were eroded down by glaciers back in the Pleistocene. This inset on the lower left is actually gravity and magnetic type data, geophysics, to see it underground. We can see these patterns through the sedimentary rocks using geophysics. Remember those pillow basalts? Way up in here, I showed you, talked about a spot up in here in upper Michigan. Okay? That's those pillow basalts right here. This is submarine eruption and stuff. Down here in southern Oklahoma, the alocogen's given the name Southern Oklahoma alocogen. But all that faulting and folding and messing up of rock layers created some fabulous traps for oil and gas. That's why that region is such a really good area down there for oil and gas deposits. And the New Madrid earthquake in the central part of the United States that broke loose and vibrated for a lot of years in the early 1800s, 1814, 15, 16, somewhere in that time period, that really rumbled the ground and changed the course of the Mississippi because the ground tilted and moved and stuff, is an old failed rift. It's a weak spot. It's an old alocogen. It's called the Reelfoot alocogen because it's located right below an old meander lake called Reelfoot Lake. So that's where they got the name from, the fishing lake. That's all that is. I could tell you a lot more about some vector things and why the Reelfoot alocogen is more susceptible to faulting and breaking as opposed to the Oklahoma one, but maybe I'll kind of leave that up in the air, and if you have any concerns or interested, I'll let you know. Because I know if a major earthquake occurs out here again, we're going to have some problems. So that's it for today. Kind of wrap up this stuff on the plate tectonics. I'll finish the rest of the story next Tuesday. We'll see you then.